I'm going to do a quick demo of some radio antenna modeling software called MMANA-GAL, and going to first look at some 80 meter antennas and talk about NVIS antennas. So I'm not an expert by any means on this software, but I'll show you what I know. This is the setup screen where we're going to define our antennas. Since this program is made in Europe, everything's in metric, but there is a way to do inches. I'll show you. First, see if we'll do our initial point of the antenna. We're defining it in like XYZ coordinate system, so we're going to say it's 0. And then let's say we're making a dipole, and let's say, for example, an 80 meter dipole. So we're just going to assume, let's define it in feet though. Let's going to say we know that each leg of the 80 meter dipole should be approximately 80 feet long, or excuse me, 60 feet long. And so a full half wave dipole would be 120 feet. So we're going to enter here, our initial X coordinate is 0. So we're going to type in 120, and then we're going to put a star and F for feet, and that converts it to meters. And now if we look, we have our antenna. So now we need to define where we're going to feed it. So we're going to feed this antenna obviously in the center, so we'll go wire 1, since this is wire number 1, and we're going to feed it in the center. Hit enter, and we go back and look at our antenna. We have our feed point in the center of our half wave dipole. Right now, well, we don't want to analyze it on 20 meters. Let me go back and yeah, we've made this an 80 meter antenna. We don't want to analyze it on 20 because that won't work too well. We're just going to select a frequency. You can type in a different frequency if you want. We can analyze it there, and we're going to analyze in free space and go. And then here's our plot. We have our antenna right here, and we have a radiation pattern in free space, but we don't live in a free space, so we're going to go to perfect, and we're going to start. And this is so when we defined this antenna, we defined it at Z0, so with no additional height baked into the antenna. So we have 10 meters added to it. You can go through here and you can add or change the height that you want to analyze your antenna at. We have 10 meters, which would be approximately 33 feet. And here we have our radiation pattern. So we see that most of our antenna radiation is going straight up, and so 2.2 is right there at 45. And then if we look at our low angle radiation, it's actually fairly poor. We're going to go back and I'm going to show you some other ways to define this. We can also, if we want to define it in lambda, so wavelength, but you can already see it's already kind of a cheat, but you can put in 0.5 because we have a half wavelength dipole from 0 to 5, half, and then we're still feeding in the center. And if we go and we look, here's our antenna. Another way we can define it is we could make two different sections. We could go 0 to 0.25, and then from 0 to minus 0.25. So we're starting at 0, and we have a quarter wavelength here and a quarter wavelength here, making in total a half wavelength dipole. But you see our feed point was still defined as the center of wire 1. Well, the beginning of wire 1 is 0, 0, which also shares 0, 0 with the other leg. So we're going to change this to wire 1 beginning. Now it has it in the. Now we have our feed point in the center of the dipole again. You could also do wire 1 end, which moves our feed point to the end of this. If we throw the analyze on this, obviously our SWR is extremely high because we don't have. It's assuming a 50 ohm impedance match, and because at the end of a half wavelength dipole, if you're going to end feed it, you're going to need some type of or something. Let's just also, you could also do wire 2. Go and look. So we move to the end of wire 2, and we could do wire 2 beginning, which is the same as wire 1 beginning. Feed points back in the middle. So those are some things you can do. We could also do real, and you can define your ground. Quick Google search is not that hard. This is Wikipedia, February of 1954. Nice. So I live about right here, so I just kind of split the difference and called it 11. And then ground conductivity or dielectric constant, you can throw in whatever you want. If you live in the desert somewhere, you could use a really low number. I believe originally it came with 13, and I think it had like 8 here. I'm gonna turn that off for now. There we go. That's a little bit better. Oh, you know why it's better? Because we're feeding it in the middle where we're supposed to. So then the question is, why is our SWR so high? Well, I just assumed exactly a quarter wavelength going out of each side, but as we all know, dipoles need to be trimmed. An interesting feature is we can optimize the antenna by clicking this optimization button, and then we can define what we want. First, we need to add all the elements, which in this case there's only one. If you're making like a Yagi antenna and you want to maximize gain, you could grab that and crank that way up. But really, I'm just going to leave all these the same and see what I can minimize that my SWR has. Say no. It's got my SWR down to 1.62, 1.61. One little glitch I've noticed in the software is right now, if I click and hold, it doesn't show me my my numbers. So, because I just ran that optimization, so if I click start and just rerun it once, it's going to rerun it with the exact same numbers. But then when I go here now, I can go through and I can mouse over and I can see what my antenna gain is going to be like. So what do we have here? Right now we have an 80-meter antenna that is 10 meters off the ground. Okay. And we see the radiation pattern is pretty much going straight up. I'm going to open up a new session. And we're going to model an 80-meter vertical antenna. Obviously, we're going to start at the ground, 0. And this time, we are going to go Z, a quarter wavelength high. But what did I just type in there? I typed in a quarter of a meter. I don't want that. What I want to do is I want to specify a quarter of lambda 0.25. Okay. So now I have my vertical quarter wavelength antenna. Where am I going to feed it? Where am I going to feed this antenna? I'm going to feed it right here. Wire 1, beginning. And let's look at it. Okay, got my feed point right here. Do we want additional height? Nope. It's going to be right on the ground. We're going to run it. I was going to try to do a demo, a poor demo, but it didn't work out. Interesting. Okay. So let me go back. What I selected here on this ground setup, on radial boundary, I have 8 ground wires. So we have a quarter wavelength up, we have 8 radials. So here's our radiation pattern. Obviously we're looking, since it's a vertical, we're looking at low angle radiation. For NVIS, we want our power going straight up. And if we look, we have a null going straight up. This would be a very poor NVIS antenna. This would be good for DX, or pretty much a DX antenna, or if you want to talk to someone further out on the edges of East or West Coast US from the central. Really don't know what else needs to be said about that. this is going back. Here's a this is our NVIS antenna where we put an 80-meter dipole 10 meters off the ground. You see our radiation pattern is going pretty much straight up, not going at low angle. And we can compare this. If I can get my screen set up. They kind of overlap a little poorly. Just have to slice. So here we have our NVIS antenna, 80-meter dipole, 10 meters off the ground, horizontal, versus a quarter wave high, 80-meter vertical with 8 ground radials, and we have our radiation pattern at low angle. Obviously, these two antennas are not going to be talking to each other. I think that's pretty much it for NVIS. If this helps anybody out, I might do some more on Yagi antennas or something else. Just let me know. And thank you, and have a good one.